today I will be talking about the cleaving of rubbers and how it's a solution, or rather a dissolution, to the emerging tire waste problem. So first of all, every year we produce about 3.4 million tons of waste tires in Europe alone, which is not a very unexpected number, seeing as most of us, I assume, drive to work with a car, a bicycle, a motorcycle, or public transport. But we also use tires for stuff like the trucks, which transport the goods to our stores, and even the airplanes with which we take a holiday, for example. And now in Belgium, we have a really good system for taking care of our old waste tires. You drive to your local garage, you switch your tires, you pay a small fee to race a tire, and they will collect all the tires and make sure that they are further processed by a different company, which in most cases is through granulation. But there's a small problem. Tires itself, the waste stream has very little contaminations because it's very well controlled, but tires themselves are quite complex. They are a rubber matrix of natural and synthetic rubber, and next to that they contain a lot of other materials such as steel wires, aramid fibers, and then a whole plethora of additives such as carbon black, silica gel, antiozonants, antioxidants, processing oils, vulcanization agents, and so on and so on and so on, which makes them very difficult to recycle. Since they are vulcanized, you cannot melt them, you cannot dissolve them, and they also don't have any condensed functional groups like polyesters, which you can then depolymerize with some kind of solvolysis. So what we looked at is, okay, but what can we do? And if you have, for example, a very old car and you leave it on your driveway for 5 to 10 years, not driving it, you'll see that on the side of your tire, you'll see these little cracks forming, as you see in the picture below, which is called ozone cracking, which is actually atmospheric ozone attacking the rubber molecules in your tire and cleaving the double bonds that are present in them through a process which is similarly used in ozonolysis. And so we looked at that and we thought, okay, what if we can actually fully exaggerate that effect and completely try to take apart a tire this way, or tire rubber, in our case, the granulate without the steel. Okay, and then what would happen with all this carbon black and the other filler materials? And so the first question I always get when I tell people this story, they always go, does that even work? And I think, in my opinion, mostly pictures say a lot more than words. So I have a few pictures here. On the left, you can see the reactor, which is filled with rubber and a solvent. In this case, I believe it's chloroform. Let me just grab a laser pointer here. You can see most of the rubber here floating on top. A little bit is attached to the steering magnet. I believe that there are some small particles of iron or another ferromagnetic metal in there, which makes it stick to the magnet. So this is before the reaction. Then we bubble ozone through it. And then after the reaction, when we let everything stand for a while, you can see actually a lot of it has sunk to the bottom. And this is actually no longer the rubber now. This is carbon black, which has absorbed a lot of the chloroform solvent and actually is a lot denser than chloroform and then sinks to the bottom, which is already a first indication that that works. The second question I always get is, okay, but then what do you get if you completely decompose a tire? And if you look at the rubbers that are present in tires, you'll see natural rubber or polyisoprene. And if you cut those at the olefinic bonds, you'll actually get levulinic acid, which is one of the platform chemicals which have been described. If you look at the other types of rubbers which are present, such as polybutadiene or polystyrene butadiene, you can get succinic acid from there, and also some other molecules with still some styrene groups in there. We've had some trouble finding these molecules with the styrene groups in there, mostly because we are under the impression that they also get cleaved from ozone if you leave them in there long enough. These molecules are mostly from the processing oils or the waxy antiozonants, which are also present in tires, but they are not our main product here. So then the following question mostly is, okay, levulinic acid, succinic acid, great, but what can you do with that? And as I already mentioned, they are platform chemicals, which means you can do a lot of stuff with them. For levulinic acid, for example, it can range from a monomer for biodegradable polymers that you can make from that, to pharmaceuticals, to solvents, and so on. And funny enough, you can actually, if you over oxidize this ketone group in levulinic acid, you can actually make more succinic acid from that. And succinic acid by itself obviously is also a platform chemical, which has a lot of applications, such as chelators, detergents, solvents, or even flavor additives. Naturally, the next question is then, okay, but how much can you actually make from a tire? Well, if we look at this funny graph that I made with a tire, this is based on, let's say, for example, for every kilogram of rubber granulate, you would completely break that down. We would get about 540 grams of product and about 460 grams of carbon black, so a little bit less than half. Of this product, about 74% is levulinic acid. So that would make per kilogram of granulate about 410 grams of levulinic acid. And the rest is succinic acid with some other molecules that we are yet to surely identify. From the carbon black, I don't know that much yet. I know that it's for a large part carbon black. I also know that there are some metals in there, and I do know that all of the zinc, which should be in this rubber granulate, is found back in this carbon black. Because we had it analyzed through ICP-MS by our friends and colleagues at LCAT from U Antwerp. What I'm looking at right now is, okay, does this reaction actually take place inside of the rubber, or actually rather at the surface? So mostly at the mass transfer. As I've hope you've been able to see before, I have a very heterogeneous system. I have rubber particles floating in a solvent which do not dissolve, and I'm trying to get a gas dissolved to get into those particles. So I took two solvents. On this graph, you can see a range of solvents that I checked on terms of swellability and how well they swell my rubber. So I took acetonitrile, which barely swells it at all, and I took chloroform, which swells it very well and was also in the range of, well, or had the property of not being flammable, which is always nice if you are bubbling oxygen and ozone through an organic solvent. I performed a reaction in there. You can see that in chloroform, which is the red graph here, actually after about 15 minutes already, the reaction starts to stagnate or plateau, which means most of it is actually already done. Whereas with acetonitrile, it actually steadily keeps going for a lot longer. Also, I've added here that here is the point actually where I've added roughly the same amount of ozone gas as I have double bonds or assume to have double bonds in my rubber, which also speaks about how efficient I can use all of the ozone gas and that I don't bubble most of it actually out again. This is just a few first results because I'm actually trying to check a lot of parameters such as particle size, temperature, and so on, because I want to build a model as to optimize the mass transfer, but I'll get back to that why in a little bit later. The last question I mostly get is, okay, isn't that like really expensive? And if we compare that to, for example, pyrolysis of tires, which is another technique that is mostly being used right now in rubber granulate, the feedstock costs the same for both, which is about 100 to 300 euros per ton. The ozone production is a lot more in my case, about 313 euros per ton, which is mostly due to the low efficiency of ozone generators. Most of them have, if you really find a good one, you'll find one with about 10% efficiency, but in most cases it will even be less than that. But the chemicals, the products that you make, they are worth a lot more also because they're already functionalized with oxygenated groups. If you compare that to pyrolysis, for example, the process is very, very cheap, which is very nice. But the compounds that you obtain is in most cases the naphtha or an oil fraction, considering that you burn off the gas fraction or the non-condensable gases to keep the process running. But the naphtha and oil fraction, either you, well, for as far as I know, feel free to correct me on that. I am not an expert on pyrolysis, but for as far as I know, they are mostly used as fuels, or they get sent to a naphtha cracker to then be further cracked to olefins. Furthermore, I have read a few papers that on the carbon black that you obtain from pyrolysis, you can actually extract some very interesting molecules such as limonene, which have quite a high value as well. I did not consider that in my ozonolysis calculation because I don't know too much about the carbon black, but I don't think there to be any limonene in there. So if I look at that very roughly, you can see actually that the percentage of how much you could gain back for every cost that you have is not that dramatically different actually in both cases. Actually, it would seem that ozonolysis is a little bit cheaper, but that's also because I'm not considering here the economics of scale, which are much better for pyrolysis in this case. What I still have planned for the future is, as I already said, I want to build a model because I want to be able to find out if I can actually also control the amount of scission, as here in a paper is demonstrated, that's natural rubber dissolved in chloroform, which is unvulcanized. But if I were actually able to control the amount of scission somewhat to be able to make longer molecules as well. Because in my case, I cut everything down completely to monomer level, but if I could get some oligomers, that could also be very interesting. And then next to that, I also want to be able to perform this entire process in a flow chemistry setup instead of just batch. Furthermore, if you have any more questions or want to collaborate on this or have any tips and tricks for me, please feel free to reach out to me or my supervisors, Christophe van de Velde and Pieter Bille. I want to thank the Capture platform once more and all of you for your attention.